So whenever we get a radical and we need to simplify it, this would not be a perfect square. So a perfect square we sometimes see like square root of 16 equals 4, square root of 169 equals 13. We even can see cube roots. For example, the cube root of 8 we say is 2, cube root of 125 is 5, because that number to the third power is that. So those simplify out and those leave us with what we call rational values. We're talking about when we can't simplify it any further. We need to be right away that can be simplified. Now, not all numbers will apply to this. Prime numbers or numbers without what we find sets or perfect squares won't do this, but we at least need to go through the process. So we start with a radical. Inside the radical we have the radicand. And then we have this n value here, which we call the index. Now in square roots, we don't typically write that number. We just take that the index is 2, like squaring a number with the exponent being 2. In cube roots, we have them as a 3. That would be the index. We go up to 4th roots, 5th roots, 6th roots, whatever we need. We have that index there, and that's an important value because that's going to tell us what the set value we need in order to simplify. So let's say we had the square root of a squared, a value squared. Well, that would be a times a. And when we have the amount of a set that the index is, so in this case 2, it allows that set to come outside the radical and just become that number. For example, 16 is 4 times 4. That set comes out to give us a value of 4. Now, not every time will something clean up as nicely as that, because let's say we have the square root of a to the third. We have 3 values. So this is going to be a times a times a. Well, I have a set of 2 here, which brings 1 out, but the other one gets left behind. So we'd say that is a root a. A root a radical a, or a square root a. We could use any of them as we go. Well, what if we have the square root of a to the 4th? Well, a to the 4th is 4 a's. That gives us 2 sets. When those 2 sets come out of the radical, we write it as a squared. So it's resorted, taken out. Well, let's go a to the 3rd times b to the 5th. So now we have factors together. A to the 3rd, b to the 5th. Would look like that if expanded out. All we're looking for here is sets. I have a set of 2, a set of 2, a set of 2. So on the outside of the radical, I write the sets that I had. An a came out, a b and a b came out, so that's b squared. What's left inside is an a and a b. They're the odd ones out. In this case, literally, they're the odd ones out because I had odd values. They did not have another value to pair up with, so we would leave it inside the radical, and that's what we're calling simplifying radicals. Now, right now, all we're looking at is sorting a's and b's. Well, what if I then threw numbers in instead and said 2 to the 3rd and 3 to the 5th? That problem still works the same as the one above. There's a set, here's a set, and here's a set. So on the outside we have a 2, a 3, and a 3. Inside, this 2 and this 3 did not have a buddy, it didn't have a friend, it stays inside. So now we put it back together. 2 times 3 times 3 is 18. And on the inside you have 6, and we'd read that as 18 root 6. So that's our goal with simplifying radicals. So let's kind of see how we play with them. We start with 128. Well, if I'm not sure about where to go factors and it's even, divide it by 2. So that's 2 and 64, still even. 2 and 32, 2 and 16. It's really even a lot of the way, so we're just going to keep taking 2's out all the way down. So it turns out this is actually 2 to the 7th. It is 7 2's. Now, we're looking at square root, so we want sets of 2, and we have 3 of them. So that means 3 sets come out, and then on the inside, that one did not have a buddy. That one's stuck inside, so that stays there. So we put this together, and it becomes 8 root 2, because 2, 2, 2 multiplies to be 8. 8 root 2 is the simplified version of the square root of 128. Now we had to go all the way down to the 2's for that one. Well, what if we went a little bit faster? What if we just looked for perfect squares? Right here, 2 and 64, I have a perfect square of 64. That's 8 times 8. And I could stop there. As long as I get a matching set, I could stop there. The 8 comes out, the 2 is left, and I still get to the same answer. So you can use the factor tree all the way down, or just look for perfect squares as we go. We'll get better with these the more we do it, but either option's available. Okay, now, suddenly we have cube root. All this means now is we need a set of 3. So first off, 128 we know from the last problem is 7 2's. So now I need sets of 3. There's a set, there's a set. So outside I'm going to write 2 times 2. Inside, that one didn't get matched up. It stays inside. So we go 4 cube root 2 is our simplified answer. Now, the cube root, 4 cube root 3 and saying 8 root 2 are very different things. Square roots and cube roots in terms of the values they represent are different. We're not worried about that right now. We just need to find a way to simplify it by matching up the sets. So let's go to 243. 243 is 3 times 81. Now, if it's square root, I'm looking for a pair of numbers. 9 and 9 is a set. They match. I don't need to factor them further. They match right there. So that 9 comes out. On the inside, 3 is left over. So that would be 9 root 3. 600. 600 is even, so I can do 2 times 300. I could do 2 times 150. I could do 2 times 75. Then that's going to be 25 times 3 and 5 times 5. So I've broken down to all these sets. This is really 2 times 2 times 2 times 5 times 5 times 3. That is the equivalent of saying the square root of 600. Now where are my sets? 2 times 2 and 5 times 5. When the sets come out, I multiply them together. It gives me 10. The leftover ones inside, I multiply together, and that gives me root 6. So I get 10 root 6. 135 is 5 times 27. Well, 5 times, or 27 turns out to be 3 3's. So because I'm looking for cube root, here's one of my sets. That comes out to be 3 cube root 5. 3 times the cube root of 108. 108 I could do is 2 times 54, which is 2 times 27. Now if I'm looking for a cube root, as I just did over here, I get 9 and 3. I get my set of 3's. So these come out. 3 times 3 cube root of, what's left is 2 and 2. So I have 4. So my answer is 9 cube root 4. Now even though 4 is a perfect square, I can't simplify that because I'm looking at cube roots. For 162, I have 81 times 2. 81 is 9 and 9, which eventually gives me 4 3's. This set comes out to be 3 times 3 4th root of 2. Now, I've finally gotten to a 4th root. All I'm changing is the number of sets that I'm looking for. And I looked for 4, I have my 4. 3 times 3 gives me 9, so I say 9 4th root 2. For the last one, we have 2,592. Well, I can divide it by 2. And get 1,296. I can divide that by 2, and that comes out to be 640 8. Divide that by 2, and that gives me 324. Divide that by 2, it gives me 162. Then I get down to 81, which is 9 and 9, and then I have 3's. Let's just rewrite this. This is 5 times the 4th root of 1, 2, 3, 4, 5 2's and 4 3's. So one set of 2's is going to come out. A single 2 gets left over because it's 5. I took out 4. There's 1 left. I have 4 3's, so that set comes out. None are left over. So on the outside, 5 times 2 times 3 is going to be 30. 4th root 2 is what I'm left with.